Hi, I'm Tom Stratton. This is Materials and Design and Engineer for the perfect material for your spacecraft. So to go through this presentation, I'll start it with the title page, and then we'll go to the presentation outline. Then I'll talk about my client, their needs. Then I'll talk about the materials categories, material comparison. Then we'll simplify it down to just one category, then to specific materials, and then the material model, and we'll finish with the conclusion. So my client is NASA, which stands for National Aerodynamics and Space Missions. It's a government-funded program that has to do with air and space exploration. They're trying to build a spaceship, and they need my help to create the outer panel of it. So what they need, the materials they need will have to be affordable. Their budget goes up to $15 million. It needs to withstand the heat of re-entry. It needs to withstand space debris. What this means is it needs to be cheap. It needs to at least range from $0 to $15 million. It needs to withstand the heat of re-entry, which means it needs to have a high heat tolerance. And then withstand the impact of space debris means it needs to have good strength and good tensile strength. So the material categories is metals, polymers, woods and fibers, and ceramics. So we'll start with metals. The hardness can range from 90 to 798 with an average of 292. The tensile strength ranges from 171 to 370 and the average is 275. The melting point can range from 674 to 1768 with an average of 1223. And finally, the cost of this can be very high. The next materials are polymers. The hardness can range from 3 to 7 with an average of 5. Tensile strength 50 to 152 with an average of 90. The melting point can go from 110 to 238 with an average of 169, and the cost is fairly low. The next is wood and fiber. The hardness doesn't say. Tensile strength ranges from 1.8 to 6.65 with an average of 4.23. The melting point doesn't say, and the cost is fairly low. The final category is ceramics, with the hardness ranges from 1023 to 2894. The average is 1762, with the tensile strength ranging from 70 to 300, and the average is 164. The melting point is very high at 1670 all the way up to 2700 with an average of 2140. The cost is fairly high, just like metals. If we look at these graphs, we can see that for hardness, ceramics are very high up in compared to the rest of them. Second place is metals, and polymers and wood and fiber have almost none. The next graph we can see tensile strength. Metals is in the lead, followed by ceramics and polymers, and wood and fiber has almost none again. Finally, we can see that the melting point of ceramics is the highest, followed by metals, and then polymers and woods are once again very low. The costs, metals and ceramics are both very high, while woods and fibers and polymers are fairly low. What this means is that metals seem like a pretty good fit, while polymers don't, woods and fibers don't, and ceramics also seem like a good fit. After some careful consideration, I've selected my specific material to be alumina. Alumina has a hardness of 1370 with a tensile strength of 300, elasticity of 307, and then finally a melting point of all the way up to 2050. The cost is medium, so it has a wide range. It mostly depends on demand. The properties of this has an ionic bond, which is also malleable, and it is a compound consisting of aluminum and oxygen. So this means that alumina is hard enough to withstand the impact of space debris, it has a high enough melting point that it doesn't burn up on re-entry, and is cheap enough to fit in our budget. This meets all three of the different criterias. A molecular level drawing of this looks something like this. As you can see, two aluminum molecules simultaneously alternate between three oxygen models. This creates a strong bond and is good for any situation. And finally, our conclusion. I thank you for your business, and I hope you find that alumina is just as good a fit as we believe it is.
Yeah, that was totally good.